Welcome to the Value of Drilling, submodule 4 of 4. In this session, we'll focus on performance benchmarking workflows, invisible lost time, and how automated rig activity detection supports KPI measurement. We'll also analyze drilling KPIs across phases, identify performance gaps, and evaluate improvements through ILT reduction and cost savings. In this submodule, we'll focus on the workflow for performance benchmarking in drilling optimization. We'll learn how benchmarking systematically identifies gaps, sets realistic targets, and delivers measurable improvements. Next, we'll define invisible lost time, or ILT, and explain how it relates to technical limit performance. This helps us understand the difference between actual operational time and the best achievable outcomes. We'll then cover automated rig activity detection. By analyzing rig states in real time, we can classify operations more accurately than traditional manual reporting and use that to build KPIs with greater precision. From there, we'll examine how drilling KPIs are applied across multiple phases, from drilling and tripping to casing, completions, and specialist activities. Each KPI provides a window into efficiency and areas for optimization. Finally, we'll evaluate how performance improvements are achieved in practice. We'll look at the results where ILT was reduced and overall cost savings were realized, showing the value of systematic benchmarking. With those objectives in mind, let's start with the case example from a multi-well project in Malaysia. This case study, published as an SPE paper, describes a Malaysian offshore campaign where benchmarking was used to drive drilling optimization. The operator faced significant performance variability between wells, despite similar geology and equipment. By applying a structured benchmarking workflow, they were able to identify invisible lost time and set technical limit targets. Here is an overview of the project. We'll start with the workflow for performance benchmarking, detailing the steps required to establish meaningful comparisons across wells. We'll then move into the concept of invisible lost time and how it relates to the technical limit. Next, we'll introduce automated rig activity detection and its role in modern KPI measurement. By classifying operations in real time, this technology provides a far more accurate dataset than traditional daily reports. We'll then apply these principles to benchmarking across phases, showing how tripping, drilling, casing, and completions can each be analyzed with consistent metrics. Finally, we'll close with a review of case studies, highlighting where benchmarking and ILT reduction led to measurable cost savings. This outline sets a roadmap for today's session. With the structure in mind, let's begin by defining the introductions and scope of benchmarking in drilling. The client had a brownfield located offshore East Malaysia. It was discovered in 1972 and commercial production started in mid-1975. There are more than 140 wells in the field, with water depths ranging from 33 feet to 160 feet. The prolonged oil price slump forces the project team to look beyond the traditional ways of avoiding any downtime. In the sustainable strategy of cutting project costs to combat the collapse in crude prices, the project team had previously committed time and resources to this endeavor. As a result, new drilling tools, technologies, and processes are continuously being developed. Although project objectives have always been obvious, results have sometimes fallen short of expectations. In some instances, and even when the intended performance objectives are achieved, the results have not been sustainable. One of the effective measures is to improve the efficiency of the well construction by measuring ongoing performance, working through performance gaps, and effectively reducing drilling time. It is a common practice to utilize the data from the comparable offset wells as a benchmark of past performance. Typically, projected well construction time has been extracted from the daily drilling report DDR. However, the purpose of the DDR is to capture a summary of daily operation, and most of the time it is not comprehensive enough to provide in-depth offset well performance. Hence, it is difficult to establish performance benchmarking because it requires specialized resources and substantial details in the operation tracking. Hence, this paper presents a methodology to properly establish performance benchmarking in the planning phase that drives the crew to perform better during execution stage. It covers the data gathering, screening analysis, and optimization done during well planning phase. The benchmarking system we're discussing is built on the Six Sigma data-driven improvement cycle, commonly referred to as the DIM-MAC process: define, measure, analyze, improve, and control. Each stage is linked to a definitive workflow designed to enable continuous drilling benchmarking across both the project team and contractors. The first stage is define. Here we focus on the characterization of invisible lost time, or ILT. By identifying and classifying ILT, we establish the scope of performance inefficiencies. The second stage is measure, where we apply automated rig activity detection and classification. This step ensures accurate, objective data collection to replace subjective reporting. Next is analyze. In this stage, we build key performance indicators for ILT quantification. This provides a measurable baseline for understanding where inefficiencies exist. The fourth stage is improve. Here, we focus on performance gap identification and setting of realistic targets to close those gaps. Finally, we reach control, which provides learning curve assurance and performance improvement sustainability, ensuring gains are embedded into future operations. Together, these DIM-MAC steps provide a structured, repeatable process for continuous benchmarking and drilling optimization. The first stage in this workflow is define, where the underlying principle is to analyze duration statistics for specific drilling processes across multiple rigs and wells. The goal is to establish realistic duration targets for each process by comparing actual performance against best practice benchmarks. Here we introduce the concept of invisible lost time, or ILT. ILT is defined as the difference between the actual operational duration and an achievable best practice target, which we often refer to as the technical limit. It's described as invisible because it doesn't appear in conventional daily or morning reports. Unlike non-productive time, or NPT, which is recorded and classified separately, ILT is hidden within what is still reported as productive time. The objective of this methodology is not only to prevent traditional NPT, but also to make productive time truly more productive by systematically eliminating ILT and meeting performance targets. ILT can be analyzed across both behavioral and technical performance categories, including slippage time, suboptimal or non-applicable procedures, unscheduled preparation tasks, substandard equipment, and in some cases, insufficient crew competency. By defining and classifying ILT clearly, we create the foundation for measurable performance improvement in drilling operations. The second stage of the workflow is measure, where we build an automated program to detect rig states and classify activities. This is done by combining two main data sources. First, we use high-frequency mud logging data, which captures second-by-second detail from surface sensors. Second, we incorporate low-frequency daily drilling reports, or DDRS, which track flat time operations. Rig state detection is essentially the process of computing exactly what the rig is doing at any given time. This is determined by analyzing sensor data for torque, rotary speed, hook height, pump pressure, mud flow rate, hook load, and depth. From these inputs, the system generates an integer channel within the time series data, which stores the computed rig state. To enable effective benchmarking, both historical offset well data and real-time well data are used. Offset well data is exported into the benchmarking program before the drilling campaign begins, creating the baseline. During operations, real-time well information is streamed into the program daily to provide real-time performance measurement. This automated measurement step replaces subjective reporting with objective, high-resolution classification. In Stage 2, we also capture flat time operations such as BHA, makeup and laydown, rig moves, and equipment pressure testing. These activities are not easily detected from high-frequency sensor data alone, so we rely on information from the Daily Drilling Report, or DDR. By combining both DDR inputs with real-time sensor data, the system can execute automated rig activity detection with minimal risk of human error. The need for manual classification is reduced, and only light quality control is required on a daily basis. The strength of this approach lies in the use of an intelligent algorithm to comprehensively define every operation in real time. Whether the rig is drilling, circulating, tripping, or performing flat time activities, each state is automatically recognized and logged. This robust automation ensures we build a dataset that is objective, consistent, and high resolution. From this foundation, we can then construct key performance indicators, benchmark performance across rigs and wells with far greater accuracy than conventional methods. With measurement complete, the workflow moves into stage 3, analyze, where we build KPIs to quantify invisible lost time. In stage 3, we move to analyze, where key performance indicators are built to quantify invisible lost time. The KPIs are computed using a combination of inputs: the computed rig state from automated detection, sensor data from the rig, the drilling plan prepared by the asset drilling manager team, and the daily drilling report compiled by the company man or well site supervisor. This integration ensures that each KPI reflects both planned expectations and actual rig performance, giving us a transparent comparison between the two. The measurement of ILT begins by analyzing each KPI at the finest level of detail. To do this, we apply histograms. A histogram is a statistical tool that shows the distribution of durations for a specific activity across wells. By plotting these values, we can identify the realistic performance envelope, highlight outliers, and define the achievable best practice target. This method transforms raw data into a clear visual representation of where ILT resides within routine operations. In stage 3, a critical step is the building of a structured KPI database. This begins at the most basic level, with each individual activity carried out on the rig. For example, drilling ahead, making a connection, tripping in, or running casing. Each activity is clearly defined to avoid ambiguity in later analysis. Once activities are identified, they are grouped into categories. Drilling activities might include on-bottom drilling or circulation, while flat time categories could include BHA makeup, pressure testing, or rig moves. By categorizing activities, we create an organized framework that enables benchmarking across wells and rigs. Looking at the scale of the KPI database that underpins our benchmarking system, the structure has 7 core activities. These represent the main operational groupings in a well's life cycle: drilling, tripping, casing, other operations, completion preparation, perforation operations, and upper completion. Across these 7 activities, we have identified around 24 categories. Categories provide the intermediate layer of organization. For example, drilling is categorized by factors such as overall performance, hole size, and section performance. Tripping includes categories like pulling out and running in. Casing categories include overall runtime and cased versus open hole. From these categories, we then build a total of 92 key performance indicators. These KPIs cover every measurable aspect of well construction, from rate of penetration, pump-to-pump time, and survey efficiency in drilling, to trip speed, casing run rate, completion preparation time, and perforation performance. The value of these statistics lies in standardization. With 7 activities, 24 categories, and 92 KPIs defined, we can measure performance consistently across rigs, wells, and campaigns. This robust database ensures transparency, enables benchmarking, and provides the statistical foundation for identifying invisible lost time and performance gaps. After the KPIs are established, individual histograms are presented to understand the statistical trends of the particular performance, distribution, P50, standard deviation, mean, and skewness. By breaking down each operation, potential good performance can be ideally identified, and consequently, a best practice of the best crew can be established in a sample data set. This allows project team to estimate technical limits and set reasonable targets for improvement. A web-based analytics tool displays KPIs, enabling the project team to easily access performance updates. The project team can visualize selected KPIs and contextual information via customized plots, charts, diagrams, or reports. Rig crews operating at a higher degree of efficiency can be highlighted, and their experience and techniques are recorded and shared with other crews. In Stage 4, Improve, based on the detailed definition of a set of KPI, the project team overlays the past offset well performance against the ongoing well's performance trends in daily tracking to investigate changes over time. Assessments are made on the ongoing well in relation to the offset wells and the year-to-date performance for the operator's reporting requirements. After an outperformed operation is identified, a new target is set based on the improved crew's capabilities, and the continuous learning curve is evaluated in order to beat the curve of the technical limit. During implementation, in addition to identifying best practices, the project team conducted comprehensive collaborations to apply new improvement methods, thereby increasing the efficiency of operations. The ability to identify the operations that contained ILT in the past has guided the project team to concentrate on these specific operations. This led to a more proactive approach in improving the drilling operation and the deployment of new technologies during the drilling process. A communication protocol is established to ensure the awareness of performance targets among all the crews. A daily performance report is sent to all project team members to outline the past 24-hour performance, identify performance gaps, and establish the next 24-hour operational performance targets. In Stage 5, Control, the project team needs to ensure that the improvements are standardized and sustained over time. Standard operating procedures are established through a systematic control plan developed by a dedicated performance engineer starting from the well planning stage. The performance engineer uses the results from the benchmarking program to optimize well planning, provide rig site advisory services, review drilling programs, coach crew members, and conduct risk management to ensure the justification of risks taken to achieve better performance. To control the improved performance, the project team ensures the targets set are clearly communicated and works to reduce the performance variations. Statistically, the reduced variation makes the performance histogram more narrow, and the goal is to make the performance histogram as narrow as possible. The main objectives are to achieve consistently high performance and a sustainable improvement curve. The wells drilled during the recent 7-well campaign offshore Malaysia utilised this workflow as part of new operator excellence and drilling the limit initiatives, which have translated to a more than 20% reduction in invisible lost time. Overall, the total well days have been reduced compared to the plan, and the 10% cost saving on authorization for expenditure AFE provided clear validation of this new drilling optimization method with the support of dedicated performance engineers. The performance of each well is optimized stage by stage as the improvement direction becomes clearer with continuous performance benchmarking. The final well had reached the technical limit time or beat the curve P10 performance. Here are some of the results from the KPI database illustrating how analytics lead to measurable performance improvements. First, let's look at stand time. The yellow region on the drilling chart represents reaming time. As we move well by well, you can see this yellow area reducing significantly. That means less reaming, more efficient hole cleaning, and shorter flat time durations. Next, we focus on bottom rate of penetration, or ROP. The charts show a clear increase in ROP from well to well, confirming that drilling efficiency has improved steadily across the campaign. Connection time also shows a downward trend. By standardizing procedures and applying lessons learned, the time taken for making connections has been reduced, improving overall drilling rhythm and consistency. Similarly, average ROP, which combines drilling progress with stand time efficiency, has increased. This is a strong indicator that improvements are being captured across multiple fronts, not just isolated events. Finally, the comparison between conventional surveys and quick survey shows that survey time has been cut in half. This not only saves time but also reduces interruptions in drilling. Together, these outputs demonstrate how a robust KPI database drives tangible operational improvement. Now let's look at the quantified results from implementing the KPI-driven benchmarking process. First, the time spent drilling out cement was reduced by 51%. This improvement reflects better planning, tool handling, and procedural discipline. Second, the on-bottom rate of penetration improved by 56.23%, while the average ROP improved by 55.31%. These are substantial gains, showing that both active drilling performance and overall drilling efficiency advanced in parallel. Third, unnecessary reaming time was significantly reduced by up to 80%. This demonstrates better hole cleaning, improved wellbore stability, and more consistent bottom hole assembly performance. Connection performance also improved markedly, with a 37% improvement resulted in an average time savings of 1.5 minutes per connection. When multiplied across a full well, this delivers hours of saved rig time. In surveying, the introduction of continuous circulation directional surveys reduced survey time by 59.17%, cutting interruptions and maintaining better drilling rhythm. Overall, invisible lost time was reduced by 20%, a significant step toward reaching the technical limit. Finally, the quality of drilling operations improved due to accelerated learning from past performance. This included better cementing quality and a reduction in differential sticking tendencies. Together, these results demonstrate clear and measurable performance improvements across both efficiency and operational quality. As we close this sub-module, let's review the objectives we set out at the beginning and reflect on how we've addressed each one. First, we aim to understand the workflow for performance benchmarking. We walked through the DIM-MAC cycle, define, measure, analyze, improve, and control, and saw how it provides a structured, repeatable method for drilling optimization. Second, we set out to define invisible lost time and its relationship to the technical limit. We explained how ILT is hidden within reported productive time and how quantifying it reveals the true gap between actual operations and best practice performance. Third, we examined automated rig activity detection, demonstrating how high-frequency sensor data and DDR inputs are combined to classify operations without human error, thereby laying the groundwork for robust KPIs. Fourth, we examined drilling KPIs across phases, from drilling and tripping to casing and completions, demonstrating how activity, category, and KPI definitions build a complete database. Finally, we evaluated the improvements resulting from ILT reduction and cost savings, reviewing case results where efficiency gains translated into faster drilling, reduced costs, and higher quality wells. This completes the learning cycle for this sub-module. This concludes sub-module 4 of 4 on the value of drilling. Please proceed to the quiz to test your understanding of performance benchmarking, ILT reduction, and KPI application. Thank you for your participation, and I look forward to continuing with you in the next stage of the training program.